Hello friends, you are watching Engineering Made Easy. I am Lalit Vasist. This video is about square law diode modulation. Here we will see the basic principle of square law diode modulation, the circuit diagram of the square law diode modulator, how it works, and also the mathematical analysis of this square law diode modulator. So let's start with the basic principle of operation. So the basic principle is, whenever we have a device having nonlinear resistance like diode and we apply two AC voltages having different frequencies, this is the condition, frequencies of the voltages applied should be different, then the amplitude modulation takes place, and in the output we get amplitude modulated wave having carrier wave and the upper sideband and lower sideband and other frequency terms also. But for practical purposes we use a tuned circuit. As in the load impedance we use a tuned circuit, LC circuit, and that tuned circuit is tuned to the carrier frequency with a narrow band. So only the carrier frequency part and two sidebands, that is the upper sideband and lower sideband frequencies, are passed. So this is the statement, the principle of operation. When two voltages of different frequencies are passed through a non-linear resistance, the amplitude modulation takes place. So in a practical modulating circuit, the frequencies other than carrier and two sideband frequencies are rejected with the help of a tuned circuit. This tuned circuit rejects other frequencies except the carrier frequency and the frequencies corresponding to two sidebands that are on both sides of the carrier frequency, the narrow band, only that is passed. So this was the basic principle. Here, as a non-linear device, we are using the diode. That's why it is known as square law diode modulation. Okay, so here you can see that with this graph, this is the diode voltage and diode current. This is the IV characteristic of the diode, you can see here, and with this characteristic it is easy to observe that this is highly non-linear. This curve is highly non-linear for low voltages, okay, and then it becomes linear. So we use this modulation process in the low voltage region of this IV characteristic of the diode, non-linear. This is non-linear, having non-linear resistance. So in square law diode modulation we make use of non-linear IV characteristic of diode. Okay, since we know that IV characteristic of diode is highly non-linear at low voltages particularly. Okay, so that's why we use it in low voltage region only. Now we will discuss the circuit diagram of square law diode modulator. This is the, here you as you now know the basic principle behind the square law diode modulation. So it's very easy to understand this circuit now. You can easily get the basic concept with this circuit. Here, as I told you that whenever through a non-linear device like diode, here we are using diode, whenever through a non-linear device like diode, two voltages, this is the carrier wave having frequency omega c, and this is the modulating signal or the message signal having frequency omega m. So these are two different frequency AC voltages, and they are applied to this nonlinear diode device. So the amplitude modulation takes place. In the output term we get many many frequency terms that include carrier wave, upper and lower sidebands, both sidebands, and other frequency components, higher frequency components also. But our purpose is just to retain the carrier and the two sideband frequency terms. Therefore we are using this tank circuit. This is the LC circuit, tuned circuit, and we have tuned this circuit to the carrier frequency. Okay, and we know that the two sidebands, lower sideband has frequency little lower than the carrier frequency, and upper sideband has a frequency little bit higher than the carrier frequency. So we are using this tuned circuit is tuned to this carrier frequency with a narrow band. So this narrow band only allows the two sidebands with the carrier frequency. So in the output we get the three terms that are desired in the amplitude modulation: the carrier wave, the carrier frequency part, and the two sidebands, upper and lower sidebands. So in the output voltage we have the modulated modulated amplitude modulated signal. Okay, so this is the concept of a square law diode modulator. So now it's time to understand the mathematical analysis, the mathematics behind the modulation process. So as we have seen and we have discussed that these two voltages are applied to the diode: Vc, the carrier part, and the carrier signal, and the modulating, that is the message signal, Vm, denoted by these are two AC voltages, and they are having different frequencies. As you can see here, that omega c and omega m are different frequencies: omega c for carrier, c for carrier, and omega m, these are angular frequencies, m for modulating signal. So Vc is Vc cos omega ct and Vm is Vm cos omega mt, and therefore this combination of voltages is applied to the nonlinear device diode here. So this total voltage, let's say SVS, so it is Vs is equals to Vc plus Vm. This whole voltage is applied, and therefore just put the values of Vc and Vm from here. Vc is Vc cos omega ct and Vm is nothing but Vm cos omega mt. So Vs is the combination of these two voltages. Now from the Vi characteristic for nonlinear diode, we know that I is equals to, this is the relationship for a nonlinear diode, IV characteristic, that I is equals to A plus B Vs plus C Vs square. If we talk about linear devices, then by Ohm's law we know that V is equals to IR, or we can say I is equals to just simply V by R. So but here it is nonlinear device, so it has square terms also. The higher terms are neglected. This may be like plus d Vs cube and other higher terms. So for keeping the things simple, we are rejecting the higher terms and taking up to square terms. So I is equals to A plus B Vs plus C Vs square. Here A, B and C are what? These are the constants. Okay, so from 1 we are now just putting the value of Vs, okay, at this places. This is the whole, this part is Vs. Just put the value of this at the place of Vs. Putting the value of Vs, we know that I is equals to A plus B. Vs is what? Vc cos omega ct plus Vm cos omega mt, and plus C Vs square. This whole part is square. Okay, now in the next step we will do nothing except in the next step we will just open this bracket. We will multiply this B with these two terms, and will apply the A plus B whole square formula. That is, A plus B whole square is A square plus B square plus 2AB. Just next step is about opening of this bracket. See here, so I is equals to A plus B, multiply B with these two terms, B into Vs, so it is BVC, this whole term, plus open that bracket, A square plus B square plus 2AB. This is just simple mathematics. So on solving this, we get I is equals to A plus, just keep your eyes on each step, A plus B Vc cos omega ct, the same part, this is same part, plus BVM cos omega mt, plus look at this now. Here what we are doing, now focus on this term, this is CVC square cos square omega ct. We will manipulate this to apply the trigonometric formula to make it simple, this expression. So it is, look at this, this is CVC square. We are just multiplying it by 2 and dividing it by 2. So expression remains the same. What we have done here in this expression, this CVC square cos square omega ct, this is CVC square cos square omega ct. Here we have multiplied it by 2 and divided it by 2, just to arrange it in this format. And the same way we have done with this, multiply it by 2 and divide it by 2. So multiplied this expression by 2 and divided it by 2. So no change. We have done it because I will tell you. And what we have done here, this is the, and no change in this expression. Okay, this is same. Okay, just I have put this 2 at this place, this 2 at this place. 2 cos omega ct. As actually we are going to use some trigonometric formulas to make the expression simpler. Hope you are getting this. So this expression is I is equals to, just focus here, a plus b, this is same, b vc cos omega ct plus b vm cos omega mt, same expression. The change is at this place only. Here use look at this, half cvc square is same, and here 2 cos square omega ct. This 2 cos square omega ct can be written as 1 plus cos 2 omega ct. Actually 2 cos square theta is nothing but 1 plus cos 2 theta. Cos 2 theta, actually we know that cos 2 theta, the trigonometric formula is cos 2 theta is 2 cos square theta minus 1. You should know this. So from this 2 cos square theta is what? Transfer it to this side. So 2 cos square theta is 1 plus cos 2 theta. 2 cos square theta is 1 plus cos 2 theta. So I have used this only. This 2 cos square, this is the theta, theta is omega ct here. So 2 cos square theta is 1 plus cos 2 theta, theta is omega ct, and the same expression with this part also. So half cvm square 1 plus cos 2 theta, this part, okay, omega m part, so 1 plus cos 2 theta. And now this expression here, we know that this is 2 cos a cos b. A is omega ct, first angle, and is the omega mt is the another angle. So 2 cos a cos b, and we know that 2 cos a cos b is nothing but cos of a plus b plus cos of a minus b. Here we know the values of a and b, so we will use it here. So it is this is cvm vcvm cvcvm and 2 cos a cos b, cos of a plus b plus cos of a minus b. Okay, this is, and this is multiplied by t. This is this because the omega ct is a and omega mt is b. So we have used this trigonometric formula. So now in the next step we will simply multiply this terms. We will multiply this term with 1 and this term with, we will just solve this. We will multiply these. Half cvc square will be multiplied by this, and this half cvm square will be multiplied by this and this, and we will open this bracket, multiply this cvcvm with these two terms. So this will be our next step, so watch carefully. So as I told you, this is just the multiplication, and we have just opened the brackets, multiplied each term. So you need not to worry much about this large expression. This is just the multiplication. Okay, so after this we are just combining these terms, as we want to separate the DC term, carrier signal, modulating signal as separate. So we are just combining the terms. This is a large expression, and we are, as per the frequency, we are combining the same expressions. Okay, so this is what this is. We are taking some terms from this big expression, a plus half cvc square and half cvm square. So cvc square, this part, half cvc square and half cvm square. This and this part are taken as, they are called as the DC term. This is the DC term. Okay, this is the DC term, and this part, this is the second part. Here we are using, this is the carrier wave, bvc cos omega ct. We know that amplitude, this is the amplitude, and cos omega ct is the carrier part. So we are taking this bvc cos omega ct. bvc cos omega ct is the carrier part. So we have separated this, have not combined it with any other expression. And the third expression is the modulating signal, bvm cos omega mt. Where is this? bvm cos omega mt. So this is the third part. As you can see here, that third part is the modulating signal. Okay, and the fourth one is the harmonics of carrier and modulating signal. These are the higher frequency terms. Fourth part is half cvc. There you observe here that this is 2 omega ct plus 2 omega mt. These are the high frequency terms. So here is the harmonics of carrier and modulating signal, half cvc square cos 2 omega ct. This is the half cv square cos 2 omega ct and half cvm square cos 2 omega mt. We have grouped these two parts together in the fourth part, and this is the harmonics of carrier and modulating signal. And now the fifth part is the upper sideband and the sixth part is the lower sideband. Upper sideband means a little bit higher frequency, omega c plus omega m. Omega c plus omega m part is the upper sideband and omega c minus omega m is the lower sideband. So the term denoting this is named as 5. Here is the term omega c plus omega m is this part, c vc vm cos omega c plus omega m. So this is the omega c, a frequency which is higher, omega m higher than the omega c. So this is the upper sideband, and lower sideband is omega m lower than the carrier frequency. Okay, this is omega m modulating frequency, angular frequency, and this is the angular frequency of the carrier wave, carrier signal. So sixth part is CVC Vm cos omega c minus omega m into t. So this sixth part. So in this expression you can see here that you can see here also that the first part was the DC term, the second part is the carrier signal, easy to notice, and third part is the modulating signal. The fourth part, this fourth part from here to here, having higher frequency terms, cos 2 omega mt and cos 2 omega ct, they are called as harmonics of carrier and modulating signal is the fourth part, and fifth part is the upper sideband. This part omega c plus omega m, and sixth part is omega c minus omega m, lower sideband. So hope you got the concept. So you can notice here that in this large expression we had 6 terms. Out of these we want to retain only 3 terms for AM modulated wave. These are the carrier wave and upper and lower sidebands. So we will retain these frequencies only. So in the load impedance that we have used this LC tuned circuit, we will tune it to the carrier frequency. The central frequency will be the carrier frequency, that is the omega c, and it will be of narrow band. It should be that narrow that it only allows the sidebands, upper and lower sidebands only. So the carrier frequency along with the 2 sidebands, upper and lower, will be retained, and other higher frequencies like other higher and lower frequencies will be rejected, like DC term, modulating signal, and the harmonics of carrier and modulating signal. They all will be rejected, and in the output we will have only 3 frequency terms: omega c, the frequency of carrier, the omega c plus omega m upper sideband, and omega c minus omega m, the lower sideband. Other will be rejected. So the output current would be, so here we are taking only the terms second, fifth and sixth, carrier, upper and lower sidebands. So this is the carrier part, BVC cos omega ct, and this one is the upper sideband, this is the lower sideband. And now just simple mathematics, like in this expression take CVCVM as common, CVCVM common in this whole expression, and in bracket we will have cos omega c plus omega m into t plus cos omega c minus omega m t. So okay, just take this part as common. Cos of a plus b plus cos of a minus b is nothing but 2 cos a cos b. Okay, we have seen it earlier. So use this cos, this is a plus b, so cos a plus b plus cos a minus b is 2 cos a cos b, and this CVCVM part is same. Okay, now BVC, take BVC cos omega ct common from this expression, BVC cos omega ct. So BVC cos omega ct is taking as common, so here this expression is 1 plus divide this by BVC cos omega ct because it has been taken common. So in the expression we will have 2CVM cos omega mt by b. Just take common this part, BVC cos omega ct, very easy. And here we will have BVC, this part, and 1 plus this part 2CVM by b. This 2CVM by b, 2CVM by b is nothing but the modulation index, denoted by MA. So write this as MA, modulation index. Okay, and this is same expression, cos omega mt cos omega ct. So this is the AM current expression for the AM current. So I think you got the concept of square law diode modulator, how we have used a non-linear resistance device like diode here, and have passed to AC voltages having different frequencies, and have used tuned circuit to retain only the three terms: carrier, upper and lower sideband frequencies. Okay, so in this way we can produce AM wave. Hope you got the concept, and for more videos you can subscribe my channel Engineering Made Easy, and if you liked it, please like my video and share it. Thanks for watching. In the next videos we will see other concepts of amplitude modulation. Thanks for watching. Have a nice day. Bye bye. Friends, for more such videos you can subscribe my channel Engineering Made Easy, and please don't forget to like and share the video if you liked it. For more detailed information you can visit my blog. See you soon in the next video. Till then, bye bye.